Get one number right, and your first bend comes off the press brake on dimension, with no test coupons and no trimming. Get it wrong, and every blank in the batch is a millimeter out. That number is the K factor. Here is what it physically is, and how to prove it on your own material. A flat pattern is never just the sum of the flanges. When you bend sheet metal, the outside of the bend stretches into tension, and the inside is squashed into compression. The outside gets longer, the inside gets shorter. So leg plus leg is always the wrong blank length. Between that stretched outside and that compressed inside, there is one layer that does neither. It is exactly as long after bending as it was flat. That is the neutral axis, and its length through the bend is the only length that survives the operation unchanged. Here is the part people miss. The neutral axis does not sit in the middle of the thickness. Bending drives it towards the inside of the bend, because the compressed side resists thinning while the outside stretches freely. On a tight bend, it sits roughly a third of the way in from the inside face. That is all the K factor is, the distance from the inside surface of the bend out to the neutral axis divided by the material thickness. 0.33 means a third of the way in. 0.5 means dead center. It is a ratio, so the number is the same in millimeters or inches. Now the arithmetic. The material consumed inside the bend allowance, is the arc length of that neutral axis, the bend angle in radians, times the inside radius plus K times the thickness. Add it to the two flat legs measured up to the start of the bend, and you have your blank. Most people never touch that formula, because CAD asks for a bend deduction instead. Bend deduction is what you subtract from the outside dimensions, the ones you measure with a tape on the finished part. Same physics, different starting dimensions. Confusing the two is the most common flat pattern error there is. So what value should you use? K depends on the ratio of inside radius to thickness and on the material. Tight bends sit low, around a third. As the radius grows past about 5 times the thickness, the metal barely thins, and K climbs towards a 0.5. The German standard DIN 6935 builds that relationship straight into its correction factor, which means one K factor typed once into your CAD settings is a guess applied to every job you run. Close on the thickness and tooling you use most. Wrong on everything else. Aluminum behaves differently to stainless. A worn V die behaves differently to a new one. That is where mystery millimeters come from. The fix takes 10 minutes and beats any chart. Cut a strip of the real material, note its exact flat length, bend it once in the tooling you will actually use, then measure the finished legs and the inside radius. Whatever K factor makes the numbers match the part in your hand is the true value for that combination. So, the neutral axis is the only length that does not change. K factor says where it sits. Bend allowance is its arc length, and bend deduction is the same answer written for outside dimensions. Build a measured table for your common material and die combinations, and flat pattern arguments end. Next time, nitrogen versus oxygen laser cutting and the real cost per meter.